Hey everyone, and thank you for being here. Myself Sumit Russell, and today I'm excited to share a story behind how Helpshift accelerated its growth by migrating to Yugabyte. Let's jump into the first slide. Who is Helpshift, right? Think about when you are using an app or playing a game and something suddenly goes wrong, right? So you need a help fast, right? Now imagine that happened to millions of users at once. That's a big problem for team behind the app, right? This is where HealthShift step in. It's a mobile first customer support platform that integrate in-app help directly into the app and game. So the user can get help right where they are. Our platform used by a leading brand like Scopely, Supercell, Netflix, and many more. So our mobile SDK is installed on 2 billion devices worldwide. It serves more than 82 million active users. And very soon we will touch 1 billion user. Now you guys seen what Helpshift does, how many user it supports, right? Uh, let's jump into the next slide about challenges with our legacy non-SQL database. Right, you've seen the scale that we operating on, which scale we are operating basically. So the challenges with our legacy non-SQL database, first is the scalability limitation. As our user base started growing rapidly, crossing hundreds of millions users, our system couldn't scale easily. There was no built-in sharding on our database. So scaling meant manual work, which became slow and difficult as we approach to billion user, right? Take a analogy, like what exactly the scalability challenges for us is like, it was like trying to upgrade a highway while traffic is still running on it, right? It that difficult to without sharding, doing the scaling part, right? um, I will talk in detail about the challenges we face because of the scalability limitation in further slide, but let's see the second challenge we face is a data inconsistency issue. So our system uses more than one database, for example, one for storing our data and another for searching it. The problem was when new information was saved, it didn't always show up in search right away, right? That means the user could be seen the older outdated result even though the data had already changed. This delay made it hard to keep the experience consistent and reliable for users. Yeah, that's about our data inconsistency issue. The last challenge that we face is data integrity concern. So our legacy database system didn't fully support ACID guarantee. This means that there was a risk of saving half done or incomplete information, especially during failure. And we've seen a couple of incidents where the transition got failed, and we led eventually that led to our data integrity concern, right? So you've seen the challenges that we face. Now let's jump into the at Hellshift, what kind of database we use. I have added one snippet here. So in this snippet, I highlighted three key databases. One is Scylla, Mongo, Postgres, and because they are a part of our ongoing migration to Yugabyte, while we also use Elasticsearch, Redshift for search and caching, respectively, the focus here is on the database we actively transitioning. Um, okay, let's talk about the Scylla. Now, for its high throughput and low latency, is deployed using the sharding architecture, and it handle approx 2.1 terabyte of data. We currently running it on version 3.2.5. Mongo is our primary database. and is configured with a replica set. It means it manages the largest data volume among the three, about 2.7 terabyte of data, and run on version 4.20. Postgres is set up on streaming replication. It store around 1.3 terabyte of data and running on version 9.6. Just a side note, I have added the version here. Um, so in future slide, you will see the comparison between. I will talk about the comparison between this database with Yugabyte. So we did the comparison with respect to these versions. So yeah. Okay, the next slide, Mongo performance challenge, right? The another major issue we face with our legacy setup was the performance, and particularly with how long it take to write the data in MongoDB. So we started seeing a significant delay in writes operation. In some cases, inserting a single record took up to 6 seconds or more, which is far too slow for real-time application, right? And then we start investigating this issue, right? It is our triggering point um, for like searching the new databases. But yeah, so we seen that the right issue that we had. So we had a call with Mongo team to investigate the performance issue, right? And the main insight from the discussion was that our Mongo collection has reached around 2 terabyte in size, and our Mongo, yeah, and in size. So given our replication set architecture, so in earlier slide I show that, right, our Mongo is set up with the replica set architecture, and this has become a bottleneck, partially impacting the writes performance. So as a long-term solution, the Mongo team right, recommended to implement a sharding, right, to distribute the load. Well, Mongo itself support the sharding, so we are also encountering other operational challenges. So we decided to take this opportunity to explore other databases that natively support sharding more efficiently. So that conversion make the beginning of search for the scalable sharding database solution. Now, in search, we focus on four key features that we critical for our platform success. So we evaluated YugabyteDB on the four critical features. First, sharding support, transition, tunable consistency, and scalable materialized view. Right. Um, let's talk about sharding. Right. So sharding is natively supported by the YugabyteDB. So we no longer have to manually partition the data or worry about the performance degradation as we scale, right? Transition. Yugabyte fully offer acidic compliant and distributed transition, which directly address our data integrity issue we encounter in our previous system. So in early slide, right, I talk about the three challenges that we face. One, scalability, that is solved by our sharding support by YugabyteDB. Second, it is fully compliant with acidic property, so it's solving our data integrity issue, right? So the two challenges that eventually get solved. Tunable consistency. So Yugabyte allow you to set the consistency level per query, enabling you to balance the latency and reliability based on the specific need of different application component, right? Such as choose a strongly consistent, right, leader read for a critical operation, and lower latency like timeline consistency follow read for a less sensitive workload. So it's especially valuable under heavy data and user load. Now, third, it's a scalable materialize view, and yeah, Yugabyte supports scalable auto refresh materialize view, and which has been a major win for us. This feature help us to upload complex query and boost up the performance, right? Particularly for analytic use cases where real-time insights matter. So, yeah. Now let's jump into the next slide. Now you've seen what are the challenges we face and on what future we evaluated the Yugabyte database. And then, yeah, so after evaluating several database, right, option, uh, Mongo, CockroachDB, Scylla, so we choose YugaDB as our distributed SQL solution based on the detailed assessment of feature critical to our success of our platform. Um, and to keep this slide concise, I haven't included the full comparison data, but Yugabyte stood out across the key area like scalability, consistency, Postgres compatibility, right? Um, so yeah, so as for the migration journey, we follow a structured phase approach. I won't go deep into each pointer here. So Helchip already given an excellent talk on the migration from non-SQL to SQL, which highly recommended to check out for a detail. But on a high level, here what our implementation look like. So we began for normalizing the data and defining the appropriate schema, right? So we the our transition is from non-SQL to SQL. So there is a lot of work that we need to do on the normalization data. So it was a difficult task, but for more detail you can check the video. Then we decide a structure that could leverage Postgres compatibility, since you got about use the Postgres under the hood, right? Second, to accommodate our previous non-SQL workload, we explore using a JSON-DB data type to handle semi-structured data efficiently. So so we haven't tried for all, but in some of the cases where we think that we should explore the JSON-DB data type. So we use in some of the scenario. We also plan secondary index migration and carefully evaluate the anti-pattern in a distributed SQL environment to avoid the performance pitfalls. Right. These steps help to ensure a smooth and future-ready transition to YugabyteDB. But again, I will iterate, go through the video that we already talk about the migration journey from non-SQL to SQL. Highly recommended. Okay, let's take a quick look at our YugabyteDB architecture, and more importantly, how it helps us to solve some real world challenges, right? So at the very top, uh, we have our applications which talk to our database through HA proxy. Now, in any distributed setup, one of the first problem we face is how to route traffic efficiently across the multiple nodes, right? That exactly where HA proxy help. It's act as our load balancer, making sure that requests don't pile up on a single node and are eventually spread across the cluster. The second challenge is managing too many open connection, right? Especially when you are dealing with high traffic. So that's where Odyssey comes in it. It's a connection pooler, and it's a great at reusing and managing connection, so that we don't overwhelm the database. This make a huge difference in the performance and the stability. Now it's worth noting, HProxy and ODC aren't part of Yugabyte itself. So when we was using, but now I think so ODC is integrated with Yugabyte DB. Uh, but is it? I think so. It's not generally available yet. So but they make sure the application can talk to database efficiently and reliable, the Odyssey and the HProxy. Moving down to the YugabyteDB cluster. So we currently run 18 node, but here I just shown the four for the clarity. Node 1 to node 3, we have master component. Um, and all these node are run the T server of data storage, and of course the Odyssey for the pool connection, right? On the fourth node, we only have a T server and Odyssey. So in short, this setup, right, that you guys are seeing, with HProxy, we are handling the load. Um, Odyssey managing our connections, and YugabyteDB powering the backend, right? So this system that scalable, reliable, and um, ready to handle production traffic, and even though we are using in a production, right? Okay, so let's talk about our cluster details, right? So we are using a Yugabyte 2.20.40. Um, we are using a AWS cloud for running this Yugabyte cluster. The Odyssey version that we are using is 1.3. Um, Again, machine type is MI6 2x large. Ubuntu Jammy OS we are using, and we are maintaining around like 18 node of cluster that manage around 4 terabyte of data. Now let's talk about some of the twin flag that we did in our production cluster, right? For their stability and for their scalability, right? YB backend OM score address. So we put 100, sorry, 1000. So this flag act as a proactive safeguard against out of memory scenario. During early stage of adoption, we experienced a cluster crash due to memory exhaust. So setting this flag help the system prioritize which process to terminate. So ensuring the scores service remain available, right? Course services remain available. A score of 1000 make it more likely that long running Postgres query will kill first, thus maintaining overall system stability, right? So it give a lot of advantage. Recommended to use YSQL minimal catalog cache preload. So these flag help us to speed up the database startup time, right? Instead of loading this entire system catalog into memory as an expensive and source heavy operation, right? So it's load only the essential part and marking the startup faster and more efficient, especially in the environment with the larger commit log, right? In those scenarios, you can use this flag. Good to have this flag. MySQL enable read request cache. Um, to enabling this help us to optimize the read performance. So for frequently access less volatile data, the database cache this result of read queries. So repeated read return faster without redundant processing. So however, it's important to note that this works best when underlying data doesn't change frequently. So you can use their this flag. Highly recommended uh, when when we have a heavy read operation and and your underlying data it doesn't changing. Right? It will enhance your performance. Yeah. YB enable read commit isolation, right? Um, so we enable this flag to address our serialized failure. Um, if we guys know, you can just read our serialized failure. It basically simultaneously transition reading the same data, right? And where you see this kind of issue. But yeah, so we start seeing the serialized failure caused by strict isolation level of Yugabyte. So instead of adding a retry logic in our application to solve this issue, right, we switch to read commit isolation. Um, so it reduces the conflict between the congruent transition and improve this query stability, especially for the high congruence workload. Okay, jump into the next slide, authentication flow. So you've seen that we are using Odyssey with the T server to manage the connection pooling, right? So we thought to add this slide because we haven't seen a good document where it is well defined how Odyssey integrated with the T server. So and how the authentication basically happened between the Odyssey and the T server. So if you see application send username password and then ODC basically hash it that username password using MD5, compare with its metadata. If it's valid, then it forward the credential to the T server. T server again hash that username password into MD5, compare its in its metadata, and if valid, user get authenticated. Right? It is very straightforward, I know, but we got to know because we faced the issue in production, and then eventually we with multiple hit and trial, we eventually find out the flow. Yeah. Now I will just give an idea about our ODC configuration. The first section, you can see the listen. It for the ODC uh, ODC server configuration, that which host to use, then which port number we should use for running the ODC server, then the basic TLS and those configuration. The storage section, YBT server, here actually we integrate with the T server. So the host, we put our T server IP here, and on which port number our T server is running. Uh, not T, so basically Postgres backend service is running 433, and target session attributes are like read write. You can put read also. You want to do read write, right? This the storage section. Now coming to the main part, where you define a database, then you define the user inside that database. Some basic configuration you do with the username, like what kind of authentication you want to use. It can be used MD5 or the plain text, right? If it's MD5, you should maintain the password in MD5. Storage is YBT server. So this value is come from the previous section that we see storage, right? Where you define which storage we need to use. Then the pool configuration, like transition, then pool size here is 20. It basically define that you should make a 20 connection with database with this user. Some of the basic configuration, client max 300. This configuration tells that this so application can make 300 connection to Odyssey, but we have full size of 20. So then eventually 300 connection use this 20 pool size. So this is the basic Odyssey configuration. Might it help you guys in your Yugabyte journey? Now let's talk about CDC architecture, right? So early you've seen that we faced three challenges. One, scalability limitation, um, the data integrity, and third is data inconsistency, right? Sharding solve our scalability issue, right? Yugabyte provide the transition support, so our data integrity issue gets solved. Now data consistency is again the biggest a challenge, right? We had So CDC, so we implemented CDC to address that issue. So our primary and the secondary database. So in our cases, primary is Mongo, and let's say Elasticsearch is the second. So maintaining the data in a sync way between primary and secondary. So to solve that, we implemented CDC. This is a high-level architecture of our implementation. So we use the Kafka Connect cluster where we deploy two connector. One is source. Source basically pull the data from the YugabyteDB, all the CDC event, put that into the Kafka topic. We created a topic for each table, and from that topic, our sync connector, S3 sync connector, pull that event from the Kafka and put into S3. So in S3, we are storing in a percute format, and eventually then onward our data analytics pipelines and those use that data. This is a high level CDC architecture, and eventually that's all our data inconsistency issue. Detail on our CDC configuration. So I just put here basic configuration of our CDC. Like we just name, you can give any name. I just put randomly name. Then connector class, database stream ID. So this stream ID you generate into Yugabyte DB for generating the or basically enabling the CDC on particular database. Then you define username, database name, task max, server name, port number, database master addresses, right? Basics. Then the table include list, like which table you want to include into a CDC pipeline, right? And topic name where you want to push this event, right? The basically topic name. Um, yeah, what achieve with YugabyteDB, right? First, the scalability. So we now supporting 4 TB of data, and we are confident that we can scale more, um, 5, 6, 7 TB of data, right? With the workload that we are assuming in future. CDC, the CDC solve our data consistency issue, right? And third is write latency, right? If you see, we was facing around 6 millisecond of um, 6 millisecond, right, latency in the write. So we that comes to around like 37 millisecond. So yeah, it's a impressive result that we got. So I have covered all the detail, right, about challenges that we face. Then eventually we choose Yugabyte as our solution for the sharding. Then what implementation we did around the Yugabyte, right? Because that what impressive result we got, right? We serving actively 800 million user, and we very soon will touch 1 billion user. um, and we have a confidence saying that we can scale around 200x capacity, right? If tomorrow our scale increase to 100 also, we can provide that to our customer without any failure. Yeah. And yeah, thank you.